This is Chapter 8, AC Steady State Analysis, Sections 1 to 4. We have some learning goals in this first 4 sections. Let's review sinusoids, certainly from Circuits 1. Let's look at sinusoidal and complex forcing functions, their representation as a phasor, and finally, bringing it back to circuits, let's talk about impedance and admittance for AC steady state circuit operation. Section 1 concerns itself with a review of sinusoids. Here we have a dimensional plot in the upper right-hand corner of a sinusoid on an axis which is labeled omega t, omega being the angular frequency in radians per second, and omega t being the argument, which has to be in radians, of course. For a single frequency sinusoid whose peak amplitude is x sub m, the period capital T, shown in the right-hand figure in the upper right, is 2 pi over omega, and by definition it means that the sinusoid replicates itself every capital T seconds. So, if you will, x of t is equal to x of t plus capital T. That's the functional definition for a period. The frequency, though, is 1 over the period. F is equal to 1 over t, therefore omega divided by 2 pi. And frequency, of course, is measured in hertz. It used to be measured in cycles per second before it became normalized to the units of hertz. And also, as we found, omega is equal to 2 pi f. In the lower right-hand corner, we have two sinusoids, the original one in red on the omega t axis, and then another one in dotted gray, which is a shifted version of the original sinusoid by some angle theta. What we say is that the dotted version leads, obviously, because it's going up first. It certainly gets the peak amplitude before the sinusoid in red gets there. So that's why we say it leads by theta, some angle theta. Or conversely, we could say it lags, the original red sinusoid lags the dotted gray sinusoid by some angle theta. We have essential identities in trigonometry and some derived identities. So let's take a look at these essential identities. Sine alpha plus beta is equal to sine alpha cosine beta plus cosine alpha plus sine beta, and of other variety of essential identities. These identities do not have to be memorized. They should be part of your notes, and those notes would then be available for you to use during a quiz or exam. We also then have some derived identities. Typically, sine alpha minus beta is equal to sine alpha cosine beta minus cosine alpha sine beta, or even more complex forms like sine alpha cosine beta equals 1/2 sine of alpha plus beta plus 1/2 sine of alpha minus beta. Again, these don't have to be memorized. What does have to be learned, though, is how to apply them, as we'll see. The applications we also have to consider include cosine omega t is functionally equivalent to sine omega t plus pi over 2, of course pi over 2 being 90 degrees, and sine omega t is equal to cosine omega t minus pi over 2. Also, the definitions within themselves, cosine omega t is functionally equivalent to minus cosine omega t plus or minus pi. It doesn't matter whether we have a phase shift of pi, 180, or a phase shift of minus pi, minus 180. Likewise, sine omega t is minus sine omega t plus or minus pi. Radians and degrees. 2 pi radians, of course, has 360 degrees in our functional definition of a complete circular extent. Or theta in radians is 180 divided by pi, if you want to convert theta from radians to theta in degrees. The accepted EE convention, though, usually does not write radian angles. It usually writes angles in degrees, and that's pretty standard. So, for example, sine omega t plus pi over 2 is equal to sine omega t plus 90 degrees. However, either form would be correct on representation of an answer. Let's take a look at this learning example. We have an original sinusoid with a peak amplitude of 1. This happens to be a cosine wave because it starts off with a peak amplitude of 1 at omega t equals 0. Then we have another sinusoid, which is omega t plus 45 degrees, and we see the phase shift in this representation here. Notice that the zero crossing occurs at 45 degrees, and the peak amplitude occurs at 135 degrees, if you will, instead of 180. So this is a shifted cosine wave. And we would say that comparing the top cosine wave to the middle cosine wave, we would say that that leads by 45 degrees. Leading means it basically, for example, gets to a peak amplitude 45 degrees earlier. It leads. Another way of writing it by trigonometric identity would be cosine omega t plus 45 minus 360. Or if you will, we could also say, and it would be correct to say that it lags by 315 degrees. So either answer is correct, either leading by 45 or lagging by 315. They are, in fact, equivalent. Another waveform here with another phase shift. This time it's minus cosine omega t plus 45. It's very similar except for the minus sign, the middle and the bottom waveforms. And what we would say there is that cosine omega t plus 45 plus or minus 180 would be a representation of that particular waveform. Or if you will, we could say that it leads the top waveform by 225 degrees, or if you will, lags by 135 degrees. Lag, of course, being the plus 45 minus 180, or essentially minus 135. And leading would be the plus 225, which is plus 45 plus 180. Here we have a problem. The problem is I've given, in this learning example, two sinusoids. V1 of t is equal to 12 sine 1000 t plus 60 degrees. And V2 is equal to minus 6 cosine 1000 t plus 30 degrees. Please remember that the argument for t is in radians, or omega, radians per second. So the frequency is in radians per second and is the factor of the time variable. Or if you will, then omega is equal to 1000. And another way of writing radians is arc seconds, or 1 over seconds, because when multiplied by time, we end up with a unitless number. The frequency in hertz is omega divided by 2 pi. So starting with 1000 for omega, dividing by 2 pi, we get about 159.2 hertz, 159.2 hertz as the frequency of this particular sinusoid. To find the phase angle, however, it's very difficult to do because one is written as a sinusoid and one is written as a cosine. So the normal way of reconciling this is to write either of these waveforms as both sines or both cosines, if you will. We can take care of the minus sign in V2 by the trigonometric identity. Cosine alpha is equal to minus cosine quantity alpha plus or minus 180. And therefore write minus 6 cosine 1000 t plus 30 degrees is equal to 6 cosine quantity 1000 t plus 30. In this case, we'll choose plus 180. We can also then change sine into cosine with cosine alpha is equal to sine alpha plus 90 degrees. And therefore, we can also do 6 cosine 1000 t plus 210, which is what we got. We can convert that as 6 sine 1000 t plus 210 plus 90 using the trigonometric identity. We like to have the phase shifts less than 180 in absolute value. That's not a hard and fast rule, but it's a good operational rule. So we can use the trigonometric identity 6 sine 1000 t plus 300 degrees, which is what we got just above, is equal to 6 sine 1000 t minus 60 degrees. Now we have a situation where we can compare for the first time the two waveforms. They both have positive amplitudes. And the only difference between these waveforms, in fact, are the phase shifts. If they did not both have positive amplitudes, you've induced another 180-degree phase shift, leading to the wrong answer. So notice that in this case, they both have positive amplitudes, the minus 6 Amplitude is now written as 6 sine, if you will. Very clearly, we could see now what the difference between the two waveforms are as a phase angle, not as an amplitude. Certainly they have a 6-unit difference in amplitude, but in this case we're interested in a phase angle, so we'll just take the difference between the two, and we find out that one way of writing it is V1 compared to V2 is 120 degrees. Therefore, the answer would be V1 leads V2 because it's a positive number by 120. Alternatively, we can take the opposite representation. Comparing V2 to V1, we get minus 120 degrees. And therefore, we would say V2 lags V1 by 120. Here we have another learning extension in which we're given I1, I2, and I3, and we're asked to produce answers having to do with whether I1 leads I2 by how much, and I1 leads I3 by how much. The first thing we notice is, of course, one happens to be a cosinusoidal wave. That's one problem. And, of course, I3 happens to have a negative amplitude. That's the second problem. So we'll reconcile it by saying cosine alpha is equal to sine alpha plus 90. And therefore rewrite I2 as 0.5 cosine 377t plus 10 degrees. The original description is now written as a sinusoid, 0.5 sine 377t plus 10 plus 90. 377t plus 45 degrees minus 377t, it should be, plus 100 degrees is equal to minus 55 degrees. And therefore, we would say I1 leads I2 by minus 55 degrees. That would be one of our answers. To move on, we could also use the trigonometric identity sine alpha is equal to minus sine quantity alpha plus or minus 180 to reconcile the negative amplitude for I3. Remember, that was one of our predicates. We have to have positive amplitudes for comparison. So here we have minus 0.25 sine 377t plus 60 is equal to 0.25 sine quantity 377t plus 60 minus 180. Or if you will, we can now form the difference between those two current waveforms. And we find it's a 165 degree difference. And therefore, that gives us our next answer and last answer. I1 leads I3 because we want to compare, in this case, I1 to I3. That's what it was asking, by 165 degrees. We don't know whether it's leading or lagging until we look at the sign of the answer. In this case, a positive 165 indicates a lead. This is section 2, sinusoidal and complex forcing functions. Here we have a typical example of what we'll be studying in this course. We have some voltage excitation, a voltage source, V of t, going into a linear electrical network. By linear, we mean it obeys the laws of linearity and superposition. So basically, it consists of passive components, not active components. And in this course, they would be resistors, capacitors, and inductors. If the independent sources are sinusoids of the same frequency, then for any variable in the linear circuit, the steady state response will be sinusoidal and of the same frequency. So frequency certainly will not change in a linear network. So for example, if V of t is equal to a sine omega t plus theta, then if we're interested in the current somewhere in the network, it would be some amplitude b times sine omega t plus some other phase angle phi. But certainly omega remains the same. To determine the steady state solution, we only need to determine two parameters, the amplitude b and the phase angle phi. So here we rewrite the circuit not as a linear electrical network of unknown description, but here we'll have a resistor in series with an inductor, a simple single loop circuit that you certainly recognize from your first course in circuits. V of t is equal to V sub m cosine omega t is our excitation function. And we'll use KVL, Kirchhoff's voltage law. So L di dt times t plus R of I of t is equal to V of t, if you will. That's our Kirchhoff's voltage law. Some of the voltage drops around the mesh have to equal, in this case, the forcing function V of t. So in steady state, I of t is equal to a cosine omega t plus some angle phi. Or if you will, I of t can also be written as a1 cosine omega t plus a2 sine omega t. That's a trigonometric identity for the sum of two angles, cosine A plus B, for example. And the derivative is a derivative that we learned in calculus, of course. The derivative of I of t as a function of t is equal to minus a1 omega sine omega t. That's the derivative of cosine. And therefore the derivative of the second term becomes just plus a2 omega cosine omega t. If you're unfamiliar with that, please review what the derivative of a cosine and a sine would be by definition. And of course, one is as a function of r, and of course one is due to the appearance of the inductor, if you will, L di dt. So now we can substitute what those things really are. In this case, the amplitudes, if you will. So we'll get minus L omega A1 plus R A2 times sine plus L omega A2 plus R A1 times cosine is equal to our forcing function in this case, Vm cosine omega t. Notice that the distributions occur across the two elements, if you will, and then they're brought together algebraically. So basically now we have an algebraic problem which we can solve. Minus L omega A1 plus R A2 is equal to 0, or L omega A2 plus R A1 is equal to V sub m. And how do we know that? Well, we know that the argument of sine omega t has to be 0 because the forcing function only has cosine in it. So that whole term, minus L omega A1 plus R A2, which is the argument of sine omega t, has to go to 0. And the other term is not going to go to 0 because it's the amplitude, if you will, V sub m, the forcing function. So by writing it trigonometrically this way, we now have an algebraic problem to solve, given by that linear equation that you see there. Or if you will, A1 can be solved. It's two equations and two unknowns. A1 is RVM divided by R squared plus quantity omega L squared, and A2 is omega L VM R squared plus quantity omega L quantity squared, if you will. And of course, in that solution, supposedly we know what R is, we know what L is, we know what omega is, and we know what V sub m is. Therefore, we can solve for A1 and A2 directly. Determining the steady state solution can be accomplished then only with algebraic tools in this case. Notice that we use the forcing functions to produce equal to 0 or equal to V sub m, and therefore we have two equations and two unknowns, and it can be solved easily. So the solution is A1 cosine omega t plus A2 sine omega t. The applied voltage is V sub m cosine omega t. And so for comparison, we can write I of t is equal to A cosine omega t plus phi. Or in this case, A1 is equal to A cosine phi, and A2 is equal to minus A sine phi. And therefore, we can also combine them as A is equal to the square root of A1 squared plus A2 squared. And the argument tan phi, which is the tangent of the angle phi, is the amplitudes minus A2 over A1. And those, of course, are gotten from our answers from the previous problem. And we can substitute them in, and we find out that the overall amplitude A then is Vm divided by R squared plus quantity omega L squared. And if you will, phi is the arctangent of omega L over R. And now we can write a more complete description. I of t is equal to, we put in what A is equal to, and we put in what the angle phi is equal to. For L not equal to 0, the current always lags the voltage as a result. And we see that as the arctangent of omega L over R. So if L is not 0, the current always lags the voltage. If R equals 0, there's only an inductor. The current lags the voltage by 90 degrees. Current lags the voltage by 90 degrees if R is a pure inductor. Solving some simple one-loop circuits can be very laborious, especially if one uses sinusoidal excitations. To make the analysis simpler, one relates sinusoidal signals to complex numbers. Then the analysis of the steady state will be converted to solving systems essentially of algebraic equations with complex variables, though. We need an essential identity in order to handle complex arithmetic, and that is the Euler identity. E to the j theta is equal to cosine theta plus j sine theta. Of course, you'll recall that j is the square root of -1, and it is our key to form a complex variable. So, v of t is equal to v sub m cosine omega t, can be written as forcing some particular function. Y of t is equal to a cosine omega t plus phi. And if v of t is equal to v sub m sine omega t in this linear electrical network, producing some response y of t, that would be a sine omega t plus phi. The cosine and sine representations will not change, but what will change, of course, is the phase angle that results phi. Okay, so let's see what some of these solutions could look like. Well, one is to write them in shorthand notation. That is, instead of writing v sub m cosine omega t, let's just write v sub m e to the j omega t, which comes from our Euler's identity. And that's the same as a e to the j quantity omega t plus phi for our forcing function. Or if you will, notice that we have the product of two exponentials, but that's what the functional definition of e to the quantity x plus y is. It's e to the x times e to the y. So we end up with e to the j theta plus multiplied by e to the j omega t, if you will. That's a typo. That should not be theta. That should be phi. If everybody knows the frequency of the sinusoids, then we can just not even worry about writing the term e to the j omega t as a result. Just assume it's there as part of the overall solution, since the frequency is well known, and therefore we could write v sub m as just a e to the j theta. Okay, so let's look at this solution again. Here we have our series RL circuit. We have our forcing function v sub m cosine omega t, and we're going to use this new formulation using complex numbers, if you will. So v of t then is equal to v sub m e to the j omega t. Notice that we've written this to begin with this way. It does not have a phase angle, so we just include the e to the j omega t term. And we're going to assume that the current that's flowing in this single loop is I sub m, an unknown amplitude, times e to the j omega t, same omega, but some phase angle phi as a result. We're going to use Kirchhoff's voltage law again, but not in its time-varying form, in its complex representation, as you'll see. This is its time-varying form for the I dt, if you will, now written as a complex number. So the I dt is j omega I sub m quantity e to the j omega t plus phi. That replaces the time variable form. And therefore, we end up with a series of linear equations, if you will, starting with the definitions L di dt plus R times I of t. We get j omega L I sub m e to the j omega t plus phi plus R I sub m e to the j omega t plus phi. Algebraically rearranging terms, quantity j omega L plus R times I sub m times e to the j omega t plus phi. And of course, we can then separate the exponentials. We'll get quantity j omega L plus R times I sub m e to the j phi e to the j omega t. We can set that equal to our forcing function, v sub m e to the j omega t. And essentially now you see why e to the j omega t is not necessarily part of the solution, because it could be divided out from both sides of that equation. And we end up with I sub m e to the j phi is equal to Vm divided by j omega L plus R divided by, now we want to normalize this, so we're going to multiply it by R minus j omega L divided by R minus j omega L, which is essentially 1, but we're trying to normalize it, and we end up with this form. Normalization means that the denominator is a real number, not a complex number. We get I sub m e to the j phi is equal to v sub m times the quantity R minus j omega L, which we picked up from the normalization, divided by R squared plus omega quantity omega L squared, which we picked up from the normalization of those terms. R minus j omega L can also be written as the square root of R squared plus omega L squared e to the arctangent of omega L over R, which is our phase angle. I sub m e to the j phi then can be substituted in that form, and we get v sub m divided by the square root of R squared plus quantity omega L squared e to the minus arctangent omega L over R, which is our phase angle. And we can get rid of the representation for the amplitude alone. We can write just the amplitude alone. Well, that's just v sub m divided by the square root of R squared plus quantity omega L squared. And of course, the phase angle we get by looking at the argument of the exponential. So the phase angle phi is minus arctangent omega L over R. Starting with v of t is equal to Vm cosine omega t. Another way of writing it is the real part of a complex number. That's v sub m e to the j omega t. The real part is equivalent to v sub m cosine omega t. And likewise, I of t, the real part of I sub m e to the quantity j omega t minus phi, is equal to I sub m cosine omega t minus phi, and that's written as now a real analytical function rather than a complex function. Here we have section 3 on phasors in chapter 8. An essential condition is that all independent sources are sinusoids of the same frequency. Because of superposition, even if they were not the same frequency, we can solve each one independently and then add up the answers as independent solutions. That comes from superposition, just like we had for DC circuits, where we had multiple DC sources. And here, that's what we said. Because of source superposition, one can consider just a single source and get the steady state response for any circuit variable, which would be given for that particular steady state single source first. So if some function, some forcing function u of t is some amplitude u sub m e to the j omega t plus theta, produces some output y of t, that would be y sub m e to the quantity j, quantity omega t plus phi. Or if you will, you can also write them as real parts in order to produce their real part representation as analytical functions. A new idea, though, then, is to separate those complex exponentials, as we've been doing up till now. So, for example, u sub m e to the j quantity omega t plus theta would be u sub m e to the j theta times e to the j omega t, and that will shorten up our solution because we would not consider e to the j omega t as being a problem, and we would go directly for the amplitudes and the phase angles. So instead of writing u is equal to u sub m e to the j theta, we'll write another way of writing the same thing, if you want, is u is equal to u sub m angle theta. In electrical engineering parlance, angle theta really means e to the j theta as a phase angle, and we'll accept the angles in degrees rather than in any other format. So u sub m angle theta is the phasor representation for u sub m quantity, cosine quantity omega t plus theta. So u sub m is the amplitude, and the phase angle is theta, and we tacitly assume that it's a single sinusoid of some radian frequency omega. So u of t is equal to u sub m cosine theta plus cosine omega t plus theta is the same way of writing it as u sub m angle theta, and the same way with the forcing function results, y, we'd get y sub m angle phi, and we could relate that back to some function of time as the real part of y sub m cosine omega t plus phi as a result. Develop efficient tools then to determine the phasor response given the input phasors. That's going to be our shortcut. So let's look at this learning example. It's our RL circuit again, single loop with V sub m cosine omega t. Well, in this case, we'll cut even closer to the chase and we'll just write it as a phasor. V sub m angle 0 as a result. Or if you want, you could also write it as V e to the j omega t, since there's no phase angle. The resulting current is I sub m angle phi, or if you will, I is equal to I e to the j omega t. And of course, we could take the real part of that at some point also. L di dt plus R I of t is equal to V. We've done this before. We can write the derivatives, if you will. L quantity j omega I e to the j omega t plus R I e to the j omega t is equal to V e to the j omega t. We have a lot of j omega t's on both sides of that equation. In terms of phasors, though, we get a much more complex representation. Since there is no phase angle, we'll get j omega Li from the first term. There's no phase angle, I just see e to the j omega t, plus Ri, again, no phase angle, equals V. Solving for I, we get I is equal to V divided by R plus j omega L. Seems to be a little bit shorter doing it with phasors. The phasor can be obtained using only complex algebra as a result. We will develop phasor representations for the circuit that will eliminate the need for writing any differential equations like L times the IDT, that's a differential equation. So it's essential to be able to move from sinusoids to phasors, but it's relatively straightforward, like A cosine omega t plus or minus theta becomes A angle plus or minus theta. A sine omega t plus or minus theta becomes A angle plus or minus theta, but because it's a sinusoid, we're using what's called cosine reference here. Since it's a sinusoid, it would be plus or minus theta minus 90 degrees. So V of t cosine quantity 377t minus 425 degrees becomes 12 angle minus 425 degrees. Simple enough. Y of t is equal to 18 sine 2513t plus 4.2 degrees becomes simply 18 angle minus 85 degrees, 85.8 degrees. You might say, well, why is it minus 85.8 degrees when it was plus 4.2? Those are equivalent. Plus 4.2 degrees is the same representation, in this case, as minus 85.8 degrees, because when you add those two together, you get 90 degrees. That's the representation of the sinusoid. So if f is equal to 400 hertz, v1 is equal to 10 angle 20 degrees, we'll get v1 of t is equal to 10 cosine 800 pi t plus 20 degrees. If v2 is 12 angle minus 60, we can get v2 is 12 cosine 800 pi t minus 60 degrees. We're using cosine reference as we've done up till now. That's why we converted 4.2 degrees to minus 85.8 degrees. Phasors can be combined using the rules of complex algebra. So for example, the product of two phasors, v1 angle theta 1 times v2 angle theta 2. The amplitudes are the product, v1, v2, and the angles add. If we divide v1 angle theta 1 divided by v2 angle theta 2, the amplitudes divide, v1 minus v2, and the angles subtract. So in multiplications, the angles add, and in the amplitudes multiply, and in division, the phase angles subtract, and the amplitudes divide. So here we come to the last section of this first representation of Chapter 8, Section 4, Phasor Relationships for Circuit Elements. For resistors, we have an easy case. V of t is equal to R times I of t, or if you will, V sub m e to the j omega t plus theta is equal to Ri m e to the j omega t plus theta. V sub m e to the j theta is equal to R I sub m e to the j theta, or if you will, V equals Ri which is the phasor representation for resistor because there is no phase shift. V is equal to Ri. It can be plotted as a linear line. That's what we would expect. So even though it's a sinusoidal excitation, the representation would still be a straight line for I and V. Phasors are complex numbers. The resistor model can have a geometrical interpretation. The voltage and current phasors are in fact collinear. So the phasor for current I and the phasor for current V will be collinear representation. In terms of sinusoidal signals, this geometrical representation that we would say is that the two sinusoids are in fact in phase, or if you will, 0-degree phase shift between voltage and current. And of course, if we plot it as functions, we would see that they would have no phase shift. Both they have the maximum at the same point in time and the zero crossings at the same point in time. They could be offset on an omega t axis by some initial angle, theta, but of course theta sub V for voltage and theta sub I for current would be the same. For an inductor, which is our other case, V of t is equal to L di dt, if you will. We can write V sub m e to the j omega t plus theta is equal to L di dt. We have to take the I dt, so we get L d by dt of the quantity I sub m e to the j omega t plus phi, or if you will in phasor form, j omega Li sub m e to the j omega t plus phi. Getting rid of some terms, we'll get V sub m e to the j theta. We've gotten rid of the e to the j omega t from both sides, is equal to j omega Li sub m e to the j phi. V is then equal to j omega Li, and that would be our representation for an inductor, the difference for the voltage and current for an inductor as a complex number. The relationship between phasors is in fact algebraic. For the geometrical review, we can use the result that the complex representation j, the square root of -1, is actually 1 angled 90 degrees, or if you will, e to the j 90 degrees. Therefore, V is equal to omega Li angled 90. And if we plot it, we would see that V and I are no longer collinear. They, in fact, are separated by 90 degrees. The voltage leads the current by 90 degrees. The current lags the voltage by 90 degrees. And in fact, you do recall that phasors can be thought of also as being rotated. So therefore, the rotation is clockwise, counterclockwise, I should say, counterclockwise in standard form. So V is obviously counterclockwise rotating ahead of I. Current lags the voltage, or voltage leads the current. And if we go to plot them, we would see that clearly. We'd see that the peak amplitude for voltage appears before the peak amplitude for current appears. So let's do a learning example with some numbers. L is equal to 20 millihenries. Notice m, little m sub h, little m h. That's millihenries. A milli is 10 to the minus 3. So that's 20 times 10 to the minus 3 henries, or if you will, 0.02 henries. V of t is equal to 12 cosine quantity 377t plus 20 degrees. In our single loop circuit, find the current. Omega is equal to 377. V is equal to 12 angle 20 degrees as a phasor. Therefore, I is equal to V divided by j omega L. I then is 12 angle 20 divided by omega L angle 90 in amperes. That's what the capital A is. The amperes are the units of the current. I then is equal to 12 divided by 377 times 20 times 10 to the minus 3, which is 20 millihenries. Therefore, at an angle of minus 70. Why minus 70 degrees? Because the angles subtract. 20 minus 90 is minus 70 degrees for the current in amperes. Therefore, reducing it back to an analytical form, a time form, I of t is 1.59, the amplitude, cosine 377t minus 70 degrees. Our other component in our RLC universe of linear components is the capacitor. And in that case, you'll recall that the current I of t is equal to C dV dt, the derivative of the voltage. So therefore, I sub m e to the j omega t plus phi is equal to c dv dt of v sub m e to the j omega t plus theta. We now have to do this in some form that would make some reasonable computational sense, and we favor phasors. So we write I sub m e to the j phi, notice we don't do e to the j omega t, is equal to j omega, which is the derivative, comes from the derivative, c e to the j theta. The derivative, if you will, of e to the j omega t, d by dt, is j omega. So therefore I is equal to j omega cv, capital V being the voltage excitation. The relationship between phasors then is algebraic. I is equal to omega CV angle 90 degrees. The representation again has it for a capacitor that the current is now leading the voltage. Remember that phasors can be thought of as either being frozen in time or rotating counterclockwise, so we say that I is obviously leading voltage in that counterclockwise sense. In a capacitor, the current then leads the voltage by 90 degrees. The voltage lags the current by 90 degrees. And if we go to plot it, we would see that the peak amplitude for current appears first before the peak amplitude for voltage. Do an example with numbers. C equals 100 microfarads. Of course, micro is 10 to the minus 6th. 100 microfarads is 10 to the minus 4 farads in scientific notation. V of t is 100 cosine quantity 314t plus 15 degrees. Find I of t. Omega is 314. V is equal to 100 angle 15 degrees, which we get from our given example. And therefore I is equal to j omega cv, which we got from our test solution. So I is omega c times 1 angle 90 times 100 angle 15 degrees. The 1 angle 90 is the representation of j, of course. J is equal to e to the j 90 degrees, or if you will, angle 90 degrees with an amplitude of 1. So therefore I is equal to 314 times 100 times 10 to the minus 6, which is capacitor value in farads, 314 being omega, times 100 angle 105 degrees. Remember that the angles add in this case. 90 degrees and 15 degrees added up to give 105 degrees. And of course the units are amperes A. Taking that phasor representation and going back to the analytical time domain description, we multiply out the amplitudes. We find out that the amplitude is 3.14. It's a cosine forcing function, so we're sticking with cosine. Quantity 314t, omega is 314, plus 105 degrees, which is our answer in amperes. So now we're going to take a look at the voltage across an inductor. L is equal to 0.5 henries, I is equal to 4 angle minus 30 degrees in amperes, F is 60 hertz. Find the voltage across the inductor. Omega is equal to 2 pi f, that's 120 pi. V is equal to j omega Li, which we found from our test solutions earlier. Therefore, V is 120 pi times 0.05 times 1 angle 90. 1 angle 90 again comes from J. J is equal to e to the j 90 degrees, amplitude of 1, angle plus 90 degrees, times 4 angle minus 30 degrees, which is our definition for current I in phasor form. Therefore, V is 75.4 angle 60 degrees. And V of t then in its analytical form in the time domain would be 75.4 cosine 377t plus 60 degrees. Now let's do an example with capacitors. Same thing, similar representation. Capacitor is 150 microfarads. The current I is a phasor is 3.6 amperes at a minus 145 degrees with a frequency of 60 hertz. Find the voltage across the inductor. That's a typo, it should be across the capacitor. Omega is equal to 2 pi f equals 120 pi. I is equal to j omega cv, is equal, which implies that V is equal to I divided by j omega c. V then is equal to 3.6, which is angle minus 145, which is I as a phasor, divided by j omega c. Omega is 120 pi. We also get j, it's written there as the last term, 1 angle 90 degrees, and c is 150 microfarads, 150 times 10 to the minus sixth. Therefore, doing the algebra, we get v is equal to 63.66, angle 235 degrees, but we convert to the analytical or temporal domain, time domain representation, as 63.66 cosine 120 pi minus 235 degrees. With that, we have finished sections 1 through 4 of Chapter 8. There may be additional problems that you might want to look at in the text. There will also be problems assigned in class.